and then joined the USGS, where he is now as a senior scientist. He's a past president of the Geochemical Society and a fellow of the Geological Society of America, American Association for the Advancement of Science, and the Society of Economic Geologists. He's served on the editorial boards of Economic Geology, the American Journal of Science, and Geochemica. He's been awarded the Presidential Rank Award, and as I understand that, that means he got an award from the President of the United States for sustained extraordinary accomplishment in his career. His research focuses on the role of geology, hydrology, ecology, and land use in regional soil geochemistry. And he has long participated in the development of critical zone science. And so I'm pleased to introduce who I think is just an all-around good guy, Marty Goldhaber.
Thank you, Tim. As he said, this is the first in a series, and as such, it's meant to be kind of a overview or a view from high altitude of some of the big issues that are facing the planet, and therefore the critical zone. So even though this is the Critical Zone Exploration Network, I've boldly put up a definition of the critical zone just as a place to start. The critical zone lies between rock and sky, where water, atmosphere, ecosystems, soils, and rock interact. It's essential to life on Earth, including food production and water quality. I think we'd all agree that there are substantial gaps in understanding critical zone processes. The questions I've kind of listed here are the cosmic ones. How does a critical zone form? How does it function? How will it change in the future? To me, the gaps in our understanding of the critical zone are particularly apparent when we try to transition from studies at local to regional to global scales. And it's, I guess, a major subtext of this talk that these gaps in understanding are alarming, given the accelerating pace of planetary change. So this is a little cartoon of the critical zone. I hope you can see my mouse pointer. Going from bedrock, or probably better stated as parent material, regolith to soil, the overlying atmosphere, and the biota that inhabit the critical zone. The reason that the critical zone is critical, of course, is that it provides what we call critical zone services, which are shown here in red, including such things as water filtration, water storage and transmission, habitat and biodiversity, carbon storage, nutrient transformation, breeding stock, and food, fiber, and fuel. The concept of critical zone services expands on the concept of ecosystem services that was introduced for describing services provided by the near natural and managed ecosystems of our planet. The reason that critical zone services are somewhat different is that they explicitly include and emphasize the coupled biotic, hydrologic, geologic, geochemical, and geomorphic processes that underpin ecosystem services. There was a very recent paper expanding on these thoughts in the Vado Zone Journal you might want to take a look at. So the reason that comprehensive understanding of the critical zone has been difficult to achieve is the complexity brought about by the fact that critical zone processes are inherently interdisciplinary, lying at the intersection of the geosphere and the biosphere. As emphasized in a paper by Amundsen and others in 2007 in the magazine Elements, the surface of our planet is the result of billions of years of feedback between biota and Earth materials. In contrast, this is probably a time in science when many scientists are increasingly specialized. Some have called it the balkanization of science, as we all kind of work in our small niches. I've already mentioned some of the biggest issues confronting critical zone science, but it's possible to state these challenges, I guess, somewhat more mechanistically. There's been a number of workshops over many years kind of thinking about Earth surface processes and what the top level issues are. I chose one set here, co-development of biota, soils, atmosphere, and climate, integration of critical Earth system processes across temporal and spatial scales, role of human activities and social trends as drivers of environmental change. This talk, although we certainly recognize that understanding the operation of the critical zone is crucial for really getting an understanding that will allow us to forecast or earthcast critical zone processes. In this talk, I'm really going to focus on the second two of these, time and space and human activities. This little slide shows a timeline extending from seconds on the left to centuries on the right. Critical zone processes extend from small fractions of a second, far to the left of this, the timeline, and geologic time, even far to the right. In order to really understand the operation of the critical zone, we need to understand the operation of a whole host of processes that span these various timescales and, in particular, how they interact. Likewise, spatial scales are a challenge for us. We need to understand processes at molecular scales that are increasingly accessed through increasingly sophisticated information, grain scales and kind of local scales. This is the soil profile, to watershed, to even basinal scales. This is the Mississippi Basin. But we clearly need to address planetary issues as well. And I think this iconic image of Earthrise, of planet Earth from space, which was photographed from Apollo 8, which entered lunar orbit on Christmas Eve, 1968, changed the perspective of much of humanity, and certainly of scientists. The picture of our lone blue planet against the black background of space, I think, probably enlarged the frame of thinking of many scientists forever. But as shown in this equally iconic picture of the night sky, the composite night sky from space, the footprint of humanity on our planet is substantial, and as we'll see, is increasing. These lights are largely powered by combustion of fossil fuels. Not only do we have a large footprint on the planet, but our world is increasingly interconnected. This is a map of airline routes showing, the density of air flights that interconnect us, and likewise global shipping routes. These interconnections have their own suite of impacts in things like invasive species and many others. So many Earth system challenges confronting this interconnected world are the consequence of anthropogenic change. The relation between humans and Earth has changed markedly over evolutionary history. Originally, we were very minor components of planetary ecosystems, and now we're major drivers of ecosystem and critical zone change on a global scale. The geologist Alexei Pavlov was perhaps one of the first to recognize the magnitude of human influence on global processes, and quoting from a 1943 article by Vernadsky, who was himself a giant, is viewed as the founder of the field of biogeochemistry. Preceding the notion of the geologic role of man, the geologist A.P. Pavlov, in the last years of his life, used to speak of the anthropogenic era in which we now live. He rightfully emphasized that man, under our very eyes, is becoming an ever-growing geologic force. So there's now actually a formal proposal that we are living in the Anthropocene, a new geologic epoch. This debate about the Anthropocene is ongoing. whether it exists, and if so, when it started, and that will eventually be resolved. But it's undeniable that whether or not we ever call it an official epic, this much is clear. Humans are forcing the Earth's environmental systems to change at a rate that is more advanced than their knowledge of the consequences. Or put more bluntly, as the Union of Concerned Scientists did, the Earth Sciences is telling the world very loudly, as loudly as we can, that there are substantial changes happening and projected to happen to our planet, whereas the decision makers, there's a disconnect between what we're saying and what the decision makers are doing, at least in the United States. That's not true globally. This is a reflection of what C.P. Snow called the two cultures, the sciences and the humanities, and he postulated that was a major hindrance to solving the world's problems. I couldn't resist putting this on. This is from just a couple days ago. Powerful Republicans, including the chair of the Science and Space panel, are now saying that Earth sciences are not hard science. And other members of the Republicans, including chairs, etc., have said similar sort of things. Earth sciences don't meet the definition of pure sciences. So this bodes poorly for our ability to influence decision making. On the other hand, it's true, as said by Neil deGrasse Tyson, a astrophysicist, the good thing about science is that it's true whether or not you believe in it. So ultimately, we'll have the last laugh. The question is, will it be in time? So what are the societal factors affecting the critical zone? They're succinctly captured in this little equation, the so-called IPAT equation, that human impact is a function of population, affluence, and technology. This is expressed mathematically, but it's actually more a conceptual equation. It was originally proposed or developed by, during the 70s, by Barry Commoner, who believed that technology was the major cause of human impact, as opposed to Paul Ehrlich and John Holdren, who focused on population. Their dialogue led to this equation, and it's been a cottage industry to analyze this equation. There's literally dozens of papers talking about the interdependencies among these variables, but nonetheless, it's a simple way for us to think about the societal factors that are influencing the critical zone. So obviously a key one is population. This is a slide showing population growth focusing on roughly the last 10,000 years during which human civilization evolved. And for much of that time, population growth was very slow. But then beginning in about the time of the Industrial Revolution, there's been an exponential growth phase, which has all kinds of consequences for our planet. This is a little bit of an enlarged version showing global population starting in 1950 and projected on out into the future. We just passed the 7 billion mark, and now we're at about 7.23 billion as of a few days ago from the U.S. Census Bureau. The implications of this are staggering, and in fact, in the last, I guess, few months, the United Nations is now projecting that the increase in population will be larger than shown here, based on changes in what they project for the population of Africa. We could hit 11 billion people by 2050. I put in this quote just because sometimes these graphs don't really convey how staggering these changes are. It's exponential growth. Every 18 days, the human population increases by a number equal to the entire human population of the world in 5000 BC. Every 5 months, it increases by a number equal to the population in the 1500s, every decade by the population in 1776, and every 2.5 decades by a number equal to the population of the Earth in 1950. In 87, the Earth welcomed its 5 billionth human. In 2013, it has over 7 billion people. It's been estimated 40% of all humans who ever lived on the planet are alive today. And coupled to this increase in population is an increase in affluence, which has led to impacts on our planet related to our consumption and utilization of materials. A lot of these impacts are fairly recent. Prior to World War II, smoke, sewage, and soot were thought of as the main environmental concerns, whereas post-World War II marked an era of a whole range of radioisotopes, detergents, plastics, synthetic pesticides, and herbicides. And one of the chemicals we're disposing of into the environment is carbon dioxide. This is a graph from the US National Climate Data Center showing in black here the CO2 concentration from 1880 onwards to something short of today, showing a dramatic increase in CO2 concentration. And the bars represent temperatures. Unfortunately, this graph, they put them in degrees Fahrenheit. Temperatures that are deviations from the average for the period 1901 to 2000. And there is a covariance between CO2 and temperature, as basic physics would suggest there has to be, based on the greenhouse gas trapping characteristics of carbon dioxide. This is an update of the CO2 concentration at the famous Mauna Loa Observatory, which Keeling started. And for the month of February, we for the first time exceeded 400 parts per million, which is the highest value probably since the end of the Oligocene 23 million years ago. So we're on a track of rapidly increasing CO2, and coupled to that is an increase in planetary temperature. This is a graph showing both terrestrial and ocean temperatures for the year 2014, which was the hottest year on record according to NOAA, and that was confirmed by other national climate agencies. Japan and England come to mind. So this shows the average for the year compared to a base period, 1981 to 2010, where the warmer colors are warmer temperatures, showing the warming of the Earth in very recent terms. This slide shows past and projected future temperatures. The historical record is shown in black, and future projected temperatures are shown with two curves here. These are modeled temperatures based on something called representative concentration pathways, which is a construct used by global modelers so that they're all starting at the same point with the same sets of assumptions. The red one here, called RCP 8.5, has sometimes been called business as usual. This is if CO2, shown in this lower left graph, were to continue on roughly the trajectory we seem to be headed towards, we'd hit something close to 1,000 parts per million in 2100, leading to a temperature increase of substantial increase to approximately 4 degrees C above long-term averages in the past. The RCP 2.6 is another extreme case where CO2 actually, CO2 mitigation processes are put in place so that CO2 actually bends around and goes down after about 2050. Both calculated temperature trends, and these are based on the order of 20 global circulation models, show an increase in temperature for the next many decades. The low CO2 model tends to level off over time, where temperature continues to increase in the high CO2 world. A number of people have suggested that 2 degrees C represents a upper limit above which there are catastrophic changes projected that humanity will suffer dramatically from. This number was somewhat arbitrary, and more recent studies seem to suggest that even at 2 degrees, there are substantial impacts that will occur. For example, the island nations, places like Vanuatu, which has been news lately, and many others are worried that they'll be underwater as a result of this level of temperature increase. Of course, temperature isn't the only thing that will change as we pump CO2 into the atmosphere and change our climate system. This is from the 5th assessment report of the IPCC, their chapter on freshwater resources, and it shows the percentage change in annual runoff, and this is for a 2-degree temperature increase, and the analysis is above a 1980 to 2010 mean. Here the colors represent relative change in percent runoff, where the warmer colors are decreases and the cooler colors are increases. The intensity of the color represents the agreement among a number of climate models in terms of the sign and intensity of the change. The climate models were coupled to hydrologic models to give this result. The white here is where there's a disagreement in the sign of of whether the runoff will increase or decrease. But it's fairly clear that the Mediterranean region, parts of Australia, the US, and even parts of South America will experience substantial decreases in annual runoff that will have significant impacts on the critical zone and on people living in those areas. One of the factors that both temperature and precipitation contribute to is soil moisture. There was just a recent paper, 2015 paper by Cook and others, evaluating the likelihood of drought over the period ending in 2100. They looked at 17 different climate models. The year that's shown in this little animation I'm about to show is the middle of a 10-year moving average. This is based on the business as usual or extreme CO2 climate scenario. And here are the colors. This is basically scaled to what's called the Palmer Drought Severity Index. The warmer colors are drought and the cooler colors are precipitation. So the warmest color is severe drought going to very wet. So let's see if this will play. This is the NASA Scientific Visualization Studio visualizing the results from this study. It's running pretty fast, but the thing you'll notice is by the end, there's a lot of red here, predicting significant drought. And in fact, the results of this study are that in the period 2050 to 2100, there's an 80% chance of mega droughts in the central and southeastern U.S. A mega drought is one that lasts for decades, something that we haven't seen in historic times. The closest thing was maybe the Dust Bowl era in the 30s, which lasted less than a decade, but had substantial impacts on the U.S. and actually led to the largest population migration in U.S. history. And so the prospect of mega droughts of the type that we haven't seen in historic times is certainly daunting. And this kind of information showing soil moisture deficits in the critical zone is something we need to think about in terms of our modeling. So, planetary temperature change will have effects across many aspects of the critical zone. This is just a map of soil organic carbon values to 1 meter depth. It's nominally a 1 kilometer grid showing total carbon in tons per hectare, where the darker browns are on the order of over 300 tons per hectare. In what I thought was quite a thought-provoking paper by Brantley and others, 12 testable hypotheses on the geobiology of weathering, they postulated that rising global temperatures will increase carbon losses from the critical zone. Their discussion of this was actually quite nuanced, and it isn't just temperature. The headline here is underlain by a complex set of processes that would impact carbon in the critical zone. But it's important to think in terms of how planetary change on the scale that we're apparently approaching will impact carbon in soils. One of the reasons that that's important is, at least at a global scale, soil is a very large pool of carbon. This number here, 4,000 petagrams, it actually probably includes frozen tundra-type soils. But nonetheless, terrestrial carbon in the nearer surface is much larger than the atmospheric pool, and changes in this terrestrial carbon pool have important implications for feedbacks in terms of planetary machinery. This issue of how planetary change will impact soil carbon, soil respiration, production of CO2, is a complex one, and it's one of those that lies squarely at the intersection of the geosphere and biosphere. There's a lot of feedbacks between soil materials, organic matter type, age of organic matter, microbiota, biota, etc. One approach that has been taken to address some of this complexity is ecosystem warming experiments. This was an earlier paper, 2001, I believe, in which the authors did a meta-analysis of 32 experiments, warming experiments, representing a range of biomes. The warming was by a range of methods, like heating coils and heat lamps and greenhouses, etc., etc. So they analyzed this data for these 33 experiments, and the results are plotted here. Soil moisture decreased, nitrogen mineralization increased, plant productivity increased, and soil respiration across these many experiments showed approximately a 20% increase average across all the experiments. So, in concert with the headline hypothesis of Brantley and others, it does appear that warming will, when applied to complex ecosystems, increase in CO2 in organic matter respiration. There's been a recent thing since then. Here's one paper by Bond, Lamberty, and Thompson, came to essentially the same conclusion using a different set of data, a different analysis. A group at the USGS think tank called the Powell Center is reanalyzing, doing another meta-analysis of soil warming experiments, many of which, the ones shown here, continued on in time and other new ones were started. So there'll be another summary of these data here soon. Another hypothesis from the Brantley et al. Paper relates to how CO2, atmospheric CO2 increase will increase the rates and extents of mineral weathering. They postulated that CO2 would increase primary productivity, which would have a range of effects, some of which would increase mineral weathering. Again, this is one of these intersection of the geosphere, biosphere, and their discussion of this topic, of course, was much more nuanced than is represents little cartoon. But nonetheless, one of the key critical zone processes, soil weathering, is likely to be impacted by the kind of global scale processes that will impact the planet if we don't do anything. It also might be pointed out that this effect of CO2 on weathering has an important time scale factor. Or over geologic time scales, the whole carbon cycle is regulated by feedbacks between hydrology and chemical weathering. In addition to the climate-related impacts of humanity, there are land use, land change impacts that are important. We profoundly modified the surface of the planet. This little cartoon map is from the American Association for the Advancement of Science Atlas of Population and Environment, and they show or argue that 40 to 50% of the ice-free land surface on Earth has been almost fully transformed by humanity, with an additional amount partially transformed. This has tremendous implications for the critical zone. Again, from the Brantley et al. Paper, land use change will impact critical zone processes and exports more than climate change. I thought I'd give a little bit of a specific example here from the U.S. On how land use change has been impacting us. This a couple of images from a paper by two of my USGS colleagues, and what they did was look at county level census data and use that to map the percentage of improved farmland or cropland by county. So these greener colors are 70 to 90% of that county is farmland, contrasting 1790 with 1997. In 1790, perhaps 90% of the population was involved, or the working population was involved in farming. So that 90% was required to feed the other 10%. Whereas in the 2000s, only 2% of the population has been involved in agriculture, and that 2% feeds the entire nation and has exported food to other parts of the world as well. Transformation of land like this has important implications for the critical zone. It's been estimated, and some research seems to show that when you convert native grassland, as was done in the Great Plains of the U.S., to farmland, you lose something on the order of 60% of the organic carbon. And I guess I meant to mention that this area, which is heavily agricultural, the Great Plains, if you recall back to the slide of drought, drought predictions are that for this area, between 2050 and 2100, there's something like an 80% chance of a mega drought, assuming we continue on the business as usual pathway of carbon increase. So, there are further implications for the critical zone of this conversion of land to agriculture. What's shown here is a map of the U.S. The polygons are hydrologic units. The colors represent water plus wind sediment erosion in gigaton or million grams per hectare per year, megatons per hectare per year. where the darker colors represent greater erosion loss. The red dots are dams that were built in the period of which the slide depicts. And this box here shows rates of water erosion, wind erosion, reservoir sediment accumulation, and net terrestrial sediment loss. So here's, excuse me, 1800. The westward expansion of the U.S. hasn't begun yet. In the decade of the 1870, you can see that already huge amounts of sediment are being lost from agricultural lands and the net terrestrial by water erosion. And dam building has increased dramatically. By 1930, the decade of the Dust Bowl, huge amounts of sediment were eroded off the land as a result of poor farming practices and a drought that lasted for a decade approximately. And the number of dams was increasing. Here, wind erosion as a result of the drought and drying up of the land increased dramatically, and terrestrial sediment is increasing behind the dams. Here, positive values are losses and negative values are increases. By 64, the number of dams and the erosion are both substantial and substantially increased. And by 1997, the number of dams is huge. And erosion has decreased, erosion rates have decreased somewhat because of lessons learned during the Dust Bowl. Practices improved. But nonetheless, I think that the really crucial thing to note here is that we have destroyed native ecosystems, such as the tallgrass prairie, that took millennia to develop and transformed the face of the nation through the impact of population increase and agriculture. The effects that I talked about for the U.S. can be generalized globally. This is a slide from a paper by Bruce Wilkinson, and it compares sediment loss globally in a number of different ways. So let's look at the right-hand graph here, which was annual loss, total terrestrial annual loss of sediment in meters per million years. This black bar is the long-term global average of sediment loss associated with geologic processes. He got to this number by analyzing the products of weathering, the sediments on the land and ocean, a database which was originally developed by a Russian Runoff and further analyzed in a wonderful book by Garrels and Christ. But if you take the long-term average, the continents have been denuded at the rate of a few tens of meters per million years. In contrast, these diamonds show the loss of material from the Earth's surface associated with human activity. This is actually based on a paper by Hook, who looked at technology over time and how much dirt an individual person could move and multiplied that by the population. It's quite an elegant analysis. And what you can see is that over time, that humanity has outstripped the natural rate of erosion of the continents, and humans are now an order of magnitude more important at moving sediment than some of all other natural processes. In a later paper, Wilkinson and McElroy quantified mean cropland soil loss from the U.S. and pasture land loss, and in a separate paper, Pimental and others estimated cropland erosion rates from Asia, Africa, South America, etc. And you can see that we are stripping the continents, we are removing Earth's surface materials at a rate that's orders of magnitude faster than the natural processes. We're also impacting nutrients. This is a map of phosphorus in the sea horizon in U.S. soils. It's based on a now completed USGS study of national soil geochemistry. The control points are shown here. And it shows Phosphorus in color-coded, where the blues are the lowest values and the red is the highest. Red is sort of 1,000 and greater. When you compare that, the sea horizon, to the surface soil, 0 to 5 centimeter, you'll see that in this area here, and partly in the Great Plains and the northern mid-continent, there's a dramatic increase in surface soil phosphorus compared to the deeper phosphorus. That increase is associated with the farming for corn. So if you actually look at these two patterns, they're very similar. This is net estimated bushels of corn per county, where the darkest green is 20,000 or greater. So phosphorus being applied in the form of fertilizer is having an impact on surface materials. Likewise, nitrogen is a nutrient that's been heavily impacted by human behavior. This shows the reactive nitrogen budget for the U.S. for 1997, a paper by Holton and others, 2012. It's divided up into natural nitrogen fixation, intentional and unintentional nitrogen fixation. So natural is biological nitrogen fixation. Intentional is dominated by the Haber-Bosch process. Haber-Bosch is a reaction of hydrogen and nitrogen gas to form some form of ammonia. And so it takes an unreactive form of nitrogen gas, and converts it to a reactive form. Unintentional is related to various forms of combustion in vehicles and utility and industry. In terms of fluxes, this intentional nitrogen fixation is currently the dominant flux of nitrogen, so that total nitrogen fixation in the U.S. for 1997 is dominated by this Haber-Bosch intentional fixation. Natural is much smaller, and unintentional makes up another portion of this. When partitioned into nitrogen and products, and that simply lost to the environment, a huge amount of nitrogen is lost to the environment, with all kinds of consequences to the critical zone and to the productivity of soils, and to things like, excuse me, dead zones, where the rivers containing a lot of this nitrogen enter the sea. And many of the sources of this additional reactive nitrogen that's produced by the Haber-Bosch process share root causes with changes in the carbon cycle, such as increased use of fossil fuels and expansion and intensification of global agriculture. Nitrogen deposition, CO2 concentrations, and temperatures are therefore increasing together. One interesting consequence of this way we've changed the nitrogen cycle is that, according to one estimate, nearly 80% of the nitrogen found in human tissues originated from the Haber-Bosch process. This shows one of the consequences of this, or manipulation of the nitrogen cycle. It's modeled atmospheric nitrogen deposition in kilograms of nitrogen per hectare per year, in a paper by Galloway in 2008. Here, the high values of nitrogen deposition in North America and Europe and South Asia are basically due to agricultural processes and combustion, fossil fuels, and whereas in parts of Africa and South America, it's actually burning of grasslands and other biotic materials. So, each one of those topics I touched on could easily be the subject of a major lecture. And so it's been, I kind of went through things fairly quickly. But a question is, where does that leave us? One attempt to summarize where we are at the moment was by Rockstrom and others, who attempted to define a safe operating space for humanity. So each one of these wedges is a process. The safe operating space is this green circle here. So for example, they estimate that for climate change, we've already exceeded the safe operating space for humanity. We're approaching it for ocean acidification, not hitting dangerous levels for stratospheric ozone depletion. The nitrogen cycle has been greatly exceeded in terms of a safe operating space. Phosphorus is approaching that. Land use is not quite at a dangerous level yet. Biodiversity loss has greatly exceeded the safe operating space. One of the things I didn't talk about is biodiversity loss. There's a number of people now who are talking about the time we're living in as the 6th great extinction, where extinction rates of organisms are exceeding those that took place during the other 5 great extinctions, such as the time at the end of the Mesozoic, when the dinosaurs disappeared. Some of the others they haven't yet quantified. But nonetheless, there's reason for concern here that we are already exceeding or at least approaching what would be a reasonable safe operating space for humanity. All these issues impact the critical zone in one way or another. And really the issue that we're faced with is that, as stated by a National Research Council report, the research establishment is poorly structured to deal with complex interdisciplinary research on large spatial scales and long-term temporal scales. These traits characterize the primary needs of an effective environmental research program. The Critical Zone Observatory Network is potentially an answer to that kind of a problem. This is from the 2011 Delaware workshop. There's a number of official and unofficial critical zone observatories that potentially can be linked together to provide the kind of spatial and temporal control that you need to span temperature zones and land use change, etc. What's needed, of course, is a way to link them together in a common framework so that the data that they're producing can be analyzed comprehensively. Excuse me. An approach to doing that has been building over time. There was a meeting in May of 2014 called Frontiers in International Critical Zone Science, which combined researchers and funders from a number of countries around the world with the idea of establishing an international critical zone observatory network. The questions that need to be addressed by a network like that are: what aspects of the critical zone explain the response, resilience, and recovery of critical zone systems to perturbations? What regions of the critical zone are most sensitive to environmental change? How can greater understanding of the past critical zone be used to improve future projections? And how can we use our critical zone science advances to manage critical zone systems? There was a follow-on meeting to this right before AGU in December of 2014, in which a smaller group of people got together and planned for how to implement this international critical zone network, and came up with a number of specific recommendations on how to accomplish that in terms of funding and collaboration. So, the ultimate point here is that we can't afford to neglect the kind of accelerating changes that we're imposing on our planet one of the great conservationists of the U.S., Aldo Leopold, stated it this way: the reaction of land to occupancy determines the nature and duration of civilization. And my personal hero, E.O. Wilson, I think is probably one of the best scientific philosophers we have today, said it this way: we are drowning in information while starving for wisdom. The world will henceforth be run by synthesizers, people able to put together the right information at the right time, think critically about it, and make important choices wisely. So I think the establishment of a critical zone observatory network which shares information and shares understanding, allowing us to cross disciplines and scales to understand the critical zone, I think is an important thing for us to focus on. So thank you very much.
Thanks, Marty. I'll say to everyone that we're taking questions through the chat box. And so if you have any questions, please type. I see right now that Sue has typed something, which I'm just going to read, Marty. And Sue says,
I can see it.
Great. Okay.
I can see it. So just to repeat it, Sue says, I'm wondering if you might expound on the difference between ecosystem services and critical zone services. Is there really a difference? Are they two non-intersecting sets, or are they two sets of two sets with intersection? So I think that they're intersecting. I think critical zone services are essentially a superset of ecosystem services. Critical zone services, I think, focus a little more heavily on the kind of geologic, hydrologic, geochemical, and even topographic underpinnings of ecosystems and how those factors are required to understand ecosystem services. Most ecologists tend to focus more on the biota, and when they focus on abiotic processes, it tends to be how are nutrients supplied and that sort of thing. And I think our critical zone perspective allows a broader kind of view of time and space. How do nutrients develop in ecosystems has been a big focus of critical zone research. And those kinds of perspectives, in addition to some of the deeper hydrologic considerations and how topography and other aspects of earth science interact to sustain ecosystems. I think all that is embodied in critical zone, in the critical zone perspective and critical zone services.
Marty, this is Tim White. I'm wondering if you could just comment a little bit. So I'm thinking back to that image you showed us a couple slides back with the safe space, and just thinking about what humanity is doing with these various portions of the planet and critical zone. And so what I'm wondering is, earlier in your talk, you mentioned, or at least a couple times, just our need to start doing something about it. And I'm curious whether your experience in USGS leadership has given you any insight into what the Department of the Interior or the survey might be thinking or doing about this, about what we're doing and where we're headed.
Well, a couple thoughts about that. One thing we've done is implement a think tank called the John Wesley Powell Center, the point of which is to address large, interdisciplinary issues. I mentioned the fact that one of those is a further analysis of ecosystem warming experiments to the present. But there's many others that are at least analyzing the data. For example, there's several related to the impact of nitrogen deposition and its impact on local, regional, and global ecosystems, and many others like that. Those are all involved with understanding, explaining and documenting the changes that are occurring on a planetary basis. The USGS is a science agency and doesn't prescribe, how things should. It provides scientific information as input to decision makers. Within the Department of the Interior, I think that there's quite a bit of thinking going on how ecosystems can be manipulated, restored, improved. And then nationally, there's many efforts along those kinds of lines. I think a lot of it is impeded by the kind of dysfunction we have in Congress. But, looking backwards, in I think it was 1962, Rachel Carson wrote an influential book called Silent Planet, was it? Anyway, Rachel Carson's book, she was attacked virulently by the industries that produce chemicals like DDT. They tried to destroy her credibility and try to cause her to lose her job, etc. But eventually, the impacts of some of those chemicals became so apparent, with birds dropping out of the sky, etc., that by 1970, we had the first Earth Day with 1 million Americans in the street worried about the impacts of humanity, of our country on the environment. And that same year we had the formation of EPA and the Clean Air Act and the Clean Water Act and RCRA and many others. So eventually the truth of what she was saying won out. And I think we're approaching a situation that has some analogies to that. I think these IPCC reports, the 4th and 5th IPCC reports, are basically benchmarks, like Rachel Carson's book, Silent Springs. And, as Neil deGrasse Tyson said, whether you believe it or not, science is always right. And I think there's no question that the impacts of what we're doing in terms of climate and land use are going to become increasingly apparent to everyone, that will reach a tipping point like we did with Silent Spring, and that there'll be a total turnaround, and all of a sudden, people like us will be kind of in high demand, as happened in the 1970s after the environmental movement of the 70s took root. So I think that's really the big picture thing. But meanwhile, it's really important for us to document the changes that are occurring and think about mitigation strategies that might address some of these issues. I talked about drought. I showed those slides about drought projected to increase. Multi-decadal, 30, 40-year droughts are projected for the future. California right now is having a 4-year drought. And as a result of that level of drought, their reservoirs are half full. They've drawn down their groundwater reserves substantially. They're implementing a whole new range of measures to conserve water. And if the drought continues, one of the great agricultural regions of the country, the Great Valley of California, will be significantly impacted. So those kinds of things, as they continue to occur, will be drivers for or action.
I don't know if you noticed because it's scrolled past, but Li Xin Jin wrote you a question. What do you think is needed to bridge the CZO watershed scale to the global scales?
Oh, that's a good question. There's not one answer to that. There's a variety. I think one of the real interesting trends that we're witnessing, in kind of the current scientific and technology environment, is the implementation of more and more sensors, improvement of sensor technology. So we're approaching a time when I think sensors that measure things of importance to us will be readily available and cheap and can be dispersed over broader areas, allowing us to look at processes that occur within a range of watersheds that might be adjacent to each other. Another trend that is apparent is the improvement in satellite sensors. There was just one launch that will measure soil moisture, I believe, on it's roughly a 10-kilometer grid, but that is a larger area than individual soil moisture sensors, but provides a bridge between data, local data, and broader scale data. And likewise, there's a range of other satellite sensors, radar sensors that can see beneath the Earth's surface. There's a whole range of things. Even the old Landsat type technology looks at the Earth over time and looks at land use change and water permanence. And those kinds of things can be studied at a variety of scales. I just have a project, my own project, with collaboration with the USGS Eros Data Center. We've developed a automated methodology, what we call a workflow, that automatically, you give it an area of the Earth you're interested in, it automatically downloads in mosaics the cloud-free data from 1984 onwards. And then if you give it a map of land cover, land use for that area, it will take the data that it's mosaic and assign a land use to it. And so you can look at land use change from roughly the 80s onward in great detail with roughly a 30-meter pixel size. So for example, we've been working in North Dakota where there's this huge explosion in hydrofracking and looked at the impact of hydrofracking on grasslands and wetlands to see, and road building actually, to see what the impacts of this incredible increase in hydrofracking wells has done to an environment that's an extremely important one from the point of view of ecology. It's one of the major migration pathways for migratory waterfowl, for example. So there's a variety of other sensors. And so there are ways to generalize from an intensively studied local watershed to larger areas. And I think those will increasingly become important as we kind of seek to generalize processes over regions. Okay.
All right. Are there any other questions? I'm sorry, Marty. I don't know well enough how to unmute everybody so we can applaud for you. So I'm just going to say thank you very much.
It was my pleasure.
I think that if there aren't any more questions, yeah, we can. Thanks again, and if there aren't any other questions, let's. Oh no, wait. Let's see what we're getting. We're getting thanks. Lots of thanks. People. Everybody's saying thank you. So I think we can end it here, unless you want to just bask in the gratitude.
No. Well, thanks for inviting me, and I'm looking forward to the rest of the series of talks.
Excellent. Thanks for everyone participating, and wait to hear about the next one. See you, Marty.
Bye-bye.